Okay, let's unpack this. We all know large language models are amazing uh, knowledge machines, but they hit a wall, right? They have, well, pretty terrible short-term memory when the context gets really, really long.
It's that computational bottleneck.
Mm.
You feed an LLM a huge document, maybe a long chat history, and the processing time, the memory needed, it just scales quadratically with the sequence length.
Quadratic scaling, so double the text doesn't just double the effort.
No, it quadruples it. It's
Right.
just not sustainable. It puts a hard limit on how much an LLM can actually understand from a big chunk of text.
Exactly. So we're stuck with these context windows, maybe a few thousand tokens, but a really dense report, that could be hundreds of thousands. So the big question everyone's asking is, how do you squish all that information down so the LLM can handle it efficiently without losing too much?
And this is where DeepSeek AI comes in with, honestly, a pretty wild idea. It kind of flips the problem on its head. Instead of messing with text compression or complex attention tricks,
Yeah.
they're proposing using the visual modality,
Yeah.
using images as the compression layer. They call it context optical compression.
Hold on. You're saying solve a language problem by turning the words into a picture first? That sounds really counterintuitive.
It does, I know. But think about it. An image, like a photo of a page of text, especially a high-res one, it packs in a ton of information linguistically, structurally.
Okay.
And when a vision language model, a VLM, looks at that image, it boils it down into a relatively small number of vision tokens. Vision systems are naturally amazing at 2D compression.
Right, so that's our mission for this deep dive then. We're getting into their proof of concept model, DeepSeek-OCR. It's basically a VLM built to test this very idea. Can an image act as a super efficient container for loads of text?
Exactly. We need to look at the architecture, how they achieve this compression, quantify those savings, the token ratios, and crucially think about what this could mean for LLM memory going forward.
So the core idea is that efficiency gain. An image of a page uses way fewer tokens than just feeding the raw digital text straight in.
It's a difference in magnitude, really. And optical character recognition, OCR, becomes the perfect testbed. If the VLM can look at the compressed visual tokens and accurately reconstruct the original text.
Then the compression worked. You got the information across.
Precisely. And we need to be clear. Like you said, there are two types of tokens here. You've got your normal text tokens that the language model part understands, maybe thousands per page.
And then you have these vision tokens, which the VLM generates from the image, maybe just 100 or two, much, much fewer.
That's the key ratio. And the DeepSeek-OCR architecture is laser-focused on maximizing this. It's got two main bits. There's the DeepEncoder, that's the engine doing the heavy compression work.
Taking the big image, spitting out few vision tokens.
Right. And then those tokens get fed into the decoder, which is a specialized language model, the DeepSeek 3B MOE A570M. Its job is just to reconstruct the text from those compressed vision tokens.
Okay, so the DeepEncoder has a tough job. It needs to handle really high-resolution images. You need the detail for text, right? But it can't use up tons of memory itself.
Exactly. Low activation memory, high compression ratio. It's a tricky balance.
So how do they prove it works? You mentioned numbers, benchmarks.
Yeah, they use the Fox benchmark. They basically map the number of text tokens in the original document against the number of vision tokens the encoder produced.
Let's get into those numbers. What's the magic ratio? How much compression can you get before things start breaking down?
Well, they found a really interesting point around the 10x mark. So if the number of text tokens was less than 10 times the number of vision tokens used,
Okay, a 10-to-1 compression.
the OCR decoding accuracy was hovering around 97%. That's almost perfect recovery. You're essentially packing 10 units of text information into one visual unit, near lossless.
97% is fantastic. That's huge compression with high fidelity. But knowing researchers, they probably pushed it further, right? What about lossy compression, like controlled forgetting?
They did. They pushed it to an extreme 20x compression ratio. So now you're really squeezing the information. 20 text tokens for every one vision token.
And what happens then? Accuracy must plummet.
It drops, yeah, but it's still around 60%. Now, 60% sounds bad for normal OCR, but think about the implication.
Right, it's not about perfect OCR anymore.
Exactly. It's proving that even when you heavily bottleneck the visual information, the VLM still retains a significant chunk of the original text. The paper connects this to simulating how memory might work over long contexts. Maybe you don't need perfect recall of everything far back.
A kind of forgetting mechanism. Interesting. And does this efficiency show up in practical tests?
Oh yeah, on the OmniDocBench benchmark, DeepSeek-OCR, in its small mode, uses just 100 vision tokens per page,
Okay.
and it beats models like JOT-OCR 2.0, which needs 256 tokens for similar results. That's more than twice as efficient right off the bat.
That's a solid gain. But they have higher performance modes too, right? The Gundam mode?
Yeah, the Gundam mode. That uses fewer than 800 vision tokens, but it's designed for really complex pages, and the comparison there is even more stark.
How does it stack up against other high-end models?
Well, take something like Miner U 2.0. It often uses nearly 7,000 vision tokens per page on average to get top-tier results.
7,000, compared to under 800.
Yep. DeepSeek is getting comparable, sometimes better, results with, like, less than 12% of the tokens. It's a massive difference in resource use.
Which translates directly to speed, I imagine.
Absolutely. Fewer tokens means faster processing. That's why they can crank out training data. They mentioned generating over 200,000 pages a day on a single A100 GPU. That's serious throughput.
Okay, so how does the DeepEncoder actually do that? Process high-res images but output so few tokens, because usually VLMs struggle there, right? Memory explodes, or they have to chop images into tiles clumsily.
Right, they often use dual towers or simple tiling, which has issues. DeepSeek's encoder is different. It's about 380 million parameters, and it uses a clever serial design.
Serial, not parallel.
Serial. They figured you need local perception for text details, but global understanding for the overall meaning. So two distinct parts, one after the other.
What's the first part?
It starts with a SAM-based component, based on the segment anything model, about 80 million parameters. It mainly uses window attention, which is efficient and great for local details, seeing individual letters, spacing, the fine structure. Think of it as the detail scout.
Got it. And that feeds into...
You get the bigger part, a CLAP large component, around 300 million parameters. This handles the broader understanding, the semantics, but it needs dense global attention.
And global attention is the expensive part computationally. Every token looks at every other token.
Exactly. If you feed it too many tokens, the memory usage goes through the roof.
So if the SAM part looks at, say, a 24 by 124 image, that must generate a lot of initial patch tokens. How do they stop that from overwhelming the CLAP part?
That's the crucial trick. That 2024 image generates 4,096 patch tokens initially. Feed that into global attention. Forget it. Your GPU melts.
So what's the solution?
They insert a critical component right between SAM and CLAP, a 16x convolutional compressor.
A bottleneck?
A very smart bottleneck. It basically takes those 4,096 tokens and instantly downsamples them spatially by a factor of 16.
Okay, 16 times smaller.
Which reduces the sequence length to just 256 tokens. Then, those 256 tokens go into the CLIP component's global attention. It's manageable. This compressor is the key to handling high-res input while keeping the expensive part under control.
That's clever. And this architecture seems flexible, too. They support different resolutions.
Yeah, they need that for different document types. They have standard native resolution modes from tiny, using just 64 tokens from a 512 by 512 image, up to large, using 400 tokens from a 1280 by 1280 image.
But what about really dense stuff, like newspapers?
Right. For those ultra-high-res inputs, they have the dynamic resolution modes, including that Gundam mode.
How does that work? Still tiling?
It uses tiling, but they seem to integrate the tiles more intelligently. The token count scales up, represented as n times 100, plus the base 256 tokens. It lets them tackle huge, dense images without breaking that core 16x compression principle on the main visual field.
This sounds like it's trained for more than just reading text off a page. They call some of it OCR 2.0 data. What's involved there?
Yeah, the training data is massive.
Yeah.
30 million PDF pages. And it covers about 100 languages, mostly Chinese and English, but importantly also 5 million pages for minority or lower resource languages.
Impressive language coverage. But deep parsing, what does that mean it can do?
It means it goes beyond transcription. It understands structure. If it sees charts or figures in the document, it parses them and outputs them as structured HTML tables. Think about how useful that is for data extraction.
Hugely useful. Any other specialized formats, technical stuff?
Oh, yeah. Chemical formulas.
Yeah.
Recognizes them and converts them into SMILES format, which is standard in chemistry. It even uses RDKit for rendering checks.
Wow.
And even abstract things like simple geometric diagrams. It can parse those visuals and represent the structure as a dictionary. It's really trying to understand the document, not just read the words.
You can see how document type would affect performance then, looking at the results.
Absolutely. Simpler documents like slides, books, basic reports, they usually have fewer than, say, 1,000 text tokens per page.
Okay.
So for those, the model does great even with low vision token counts like 64 or 100. It's comfortably within that efficient 10x compression ratio.
But then you hit the dense stuff.
Like newspapers.
Yeah.
Those can easily have 4,000 or 5,000 text tokens crammed onto one page. To get decent quality OCR there, you have to use more vision tokens, pushing past the 10x ratio into those Gundam modes.
It really shows the trade-off. Fidelity costs tokens, especially when the source is information dense.
Exactly, which loops us back to the big theoretical idea, using this optical compression to tackle the LLM long context problem.
Simulating memory, right?
Yeah, simulating how human memory seems to work. We don't remember everything perfectly forever. Distant memories get fuzzier. We retain the gist. LLMs currently try to remember everything perfectly within their window, which is computationally brutal.
The paper had that nice analogy, right? Figure 13. Memory decay over time is like visual perception getting weaker with distance, or crucially, with lower resolution.
That's the core insight for a potential system. Recent stuff, the important context you need now.
Keep it sharp.
Exactly. Represent it with a high-resolution rendered image. That means lower compression, maybe close to that 10x ratio, using more vision tokens. The LLM remembers it clearly.
And the older stuff, the context from way back.
You progressively forget it by downsizing the image. Render it at a much lower resolution. This forces the DeepEncoder into a higher compression mode, maybe near that 20x ratio.
So it uses far fewer tokens.
Far fewer. The model only retains the main points, the gist, just like our fuzzy long-term memories. And the computational cost drops dramatically.
That feels like a much smarter way to handle long context than just trying to build ever bigger memory banks. It's dynamic.
It's a potential path towards theoretically unlimited context. You're constantly balancing information richness against computational cost, using visual resolution as the knob.
So DeepSeek-OCR isn't just a tool, it's a validation. It shows a model can decode text from significantly fewer vision tokens, proving the visual pathway works for this kind of compression.
Definitely. It validates that 10x plus compression is feasible. It's practical for OCR, yes, but it's also a signpost for future architectures.
But the authors themselves say this isn't the final word, right? OCR alone isn't the full test. They mention future work.
Yeah, they're quite clear. They plan to move towards digital optical text interleaved pre-training.
Meaning training the model from scratch with both text and its visual representation mixed together.
Exactly. So the model doesn't just learn to decode an image back to text. It learns the inherent connection between visual density, layout, and the language itself right from the start.
And they also mentioned needle in a haystack testing.
Right. Those tests where you hide a tiny piece of information in massive context and see if the model can find it, that would really stress test how well this optical compression retains specific facts, not just the gist.
So the really provocative question for you, the listener, is what happens when this kind of optical compression isn't just an OCR task, but it's fundamentally baked into how the LLM perceives and processes information from day one? What new capabilities unlock then?
That's the exciting unknown. This is definitely research to watch, and if you want to play with the current model, the codes and weights are public.
Yeah, check it out at github.com/deepseek-a deepseek-ECR. Really fascinating stuff, pushing the boundaries of LLM memory.